Hello, everyone. I am Thomas Weingart, a member of Group 2 for ME 4056 and a part of Burdell Incorporated, and today I'll be talking to you about our lab. The team has been tasked by Generative Energy Systems Incorporated to characterize their engine's mechanical, fluid, and energy properties. The team has also been instructed to choose controls for optimal power generation, which is the team's end goal. The engine system is comprised of multiple sensors and components. The setup is equipped with a force transducer and an encoder, both of which are hooked up to the Elvis 3 LabVIEW board, which collects the data from the sensors and displays it in the dashboard of the computer program. The force transducer is connected to a weight plate, which is used to hold weights while the force transducer is calibrated. The engine's main component that will be dealt with during the study is the flywheel. In our testing, our team will test the engine with 1 and 4 flywheels to see if greater mass will improve performance. This affects the moment of inertia of the entire engine system. The team had 3 main goals for the first week of testing. First, the team needed to determine the physical dimensions of the IC engine, such as bore diameter, the height at top dead center, and the height at bottom dead center. These will be used in later calculations when the team calculates the theoretical work done by and to the air and the power and compression strokes. The second goal is to construct a model that represents the operation of the IC engine. The team will achieve this by using the work kinetic energy theorem along with a few assumptions or system changes, such as removing the head and removing pressure injections. The third and final goal of the team is to determine the torque caused by friction, as well as find the moment of inertia of the entire system. The frictional torque will be used to help determine what frictional model the team will use in later stages of the lab, which correlates to the relationship between voltage and frictional torque. The moment of inertia is vital in the team's mathematical model and will be important in later calculations. To achieve the team's first goal, the engineers will use calipers and a scale to determine the physical characteristics of the IC engine, the flywheels, and the weights used in calibration. In the first week of the lab, the team will remove the head of the engine, which will allow the mathematical model to simplify to only having the work of friction and the motor. This will help the team achieve their second and third goal, since this determines the frictional torque, the moment of inertia of the system, and the motor work. All of these will be used in future weeks, and since the work done by friction will not change as the system becomes more complex, the team will have one less variable to worry about. The physical dimensions of the IC engine were determined by using a set of calipers. The bore volume was the subject of interest, seen circled in the image to the left. Throughout the engine cycles, the volume of that cavity changes, and there are two volumes that are of particular interest, the volume at top dead center and the volume at bottom dead center. These represent the volumes at the start or finish of the power and compression strokes and are used to calculate the theoretical work of air, which will be used in later weeks of the study. The dimensions found by the team are recorded in the table as seen on the slide. The bore diameter and the respective depths will be used to calculate the volume of the chamber at top dead center and bottom dead center.
To ensure accurate measurement of forces, it is essential to calibrate the transducer. So 6 different methods was used to calibrate the force transducer. So we sequentially placed and removed each mass on the weight plate while recording the corresponding output voltage from the transducer. Then we plotted the recorded data on a graph and performed linear regression to calibrate the transducer. So the results of the calibration are shown in the figure, which display the linear regression equation and the uncertainty bound. So these values demonstrate that our force transducer is accurate and reliable for use in our experiment. Let's discuss the calculation of torque friction using the work energy balance method. First, we assume that the work done by the piston and air is zero. This is because the system has large enough flywheels, and there's no head, which means there's no air pressure. Also, to set up the system, we powered the electric motor and ensured that the flywheel runs at a constant velocity. In the modeling equation, the work done by the motor and the work done by friction are opposite and cancel each other out. To calculate the work done by the motor, we used numerical integration. To calculate the torque friction, we divided the data into two parts, the section from A to the B and the steady state portion from B to the C, considering only the part where the system was at a constant velocity. Using the midpoint rule, we calculated the work done by the motor from the data obtained. By using these two calculations, we were able to determine the torque friction and its uncertainty, as shown in the table. Visualizing the plots of angular velocity and torques provides a better understanding of the system's behavior. The plots shown below represent the result obtained from a system with zero point 0.9 voltage and 4 flywheels. To determine the expected value of torque friction, we chose to use the Newtonian friction motor. This was because the experimental torque friction did not appear to be constant. From the experimental torques, we obtained an interpolated equation that can be used to predict the torque friction in the future. To calculate the inertia of a flywheel, we assume that the angular velocity at the start is zero. The work done by the piston is negligible because of the large size of the flywheel and there is no air pressure, which means that the work done by the air is zero. Based on these assumptions, we can use the torque friction obtained from the previous slide to calculate the inertia of the flywheel. On the right side of the slide, we have a plot for zero point 0.9 voltage and 4 flywheels, including the acceleration from rest. In summary, by making certain assumptions and using the appropriate formula, we can calculate the inertia of the flywheel. However, if we calculate the formula using the data we have collected, it will give us the combined value of the inertia of the flywheel and the inertia of the system. Therefore, we need to subtract the inertia obtained by combining the system with four flywheels from the inertia obtained by combining the system with only one flywheel. This allows us to eliminate the inertia of the system and determine the inertia of the flywheel alone. This is the plot of averaged angular velocity versus angular position in the xy plane. This is a plot of average torque versus angular position represented in the xy plane, similar to the previous slide.
In order to calculate the theoretical moment of inertia of the flywheel, a CAD replica of the flywheel plate was modeled through SolidWorks, and from the associated mass properties, the moment of inertia can be determined. Modeling a single flywheel of 1032 grams, the theoretical moment of inertia is 0.00266 kilogram meter squared. The experimental flywheel inertia was obtained through the first equation for both the single flywheel and the four flywheels, including the system inertia. An EPA analysis was performed to calculate the uncertainty bounds of the experimental flywheels. The uncertainty for the flywheels without the system is determined by taking the minimum value between the uncertainty of the single flywheel and the four flywheels. The uncertainties for the different voltages are displayed in this table. All theoretical iFly values fall within bound, and an absolute difference was calculated to illustrate the most representative flywheel inertia value. In this case, the iFly of 0.0028 corresponding to the 0.6 volt setting is the closest value to the theoretical. Based on our week 1 results, it was observed that the frictional torque decreases with increasing mass for voltages of 0.3 and 0.6 volts, but it remains relatively constant for 0.9 volts. The use of four flywheels greatly increases the moment of inertia for the system, and an increase in angular velocity results in an increase in the frictional torque. Furthermore, the calculated moment of inertia for the flywheel is greater than the theoretical value. This is possibly due to the unaccounted masses and friction in the system. For the second week of lab, we added the head of the engine, which adds the W air variable into the work kinetic energy equation, which can be rearranged to solve for W air experimentally. A theoretical calculation can also be performed in order to compare the two values. The unmodeled effects can be quantified through an absolute difference, such as W discrepancy. For the third week of lab, the engine is in full operation. Since W air is known, pressure injection can be added. The goal will be to maximize engine power output to generate electricity, as well as to determine the work done per full representative cycle. The power will be maximized by tuning the supply pressure and adjusting the voltage to fix a desired motor speed.